Hi, my name is Connor Bush, and today we're going to look at this reactor here um, and derive some equations for non-steady state mass flow. For this first part, we're going to derive two differential equations, one that relates the change in the height of this water level here with respect to time, and then also the temperature inside of the reactor. So first we need to kind of look at a few different aspects of this reactor. Um, we know that there's a flow rate going in and then a specific temperature going in. At the bottom, there's a flow rate going out called Q out. There's this area of the reactor that remains constant no matter what the water level is. We'll label that as A, and then the height we'll call lowercase h. So the problem gives us a bunch of initial values for these variables, but we'll input those later when we go into Python and plot the different relationships. So for Q out, this can be expressed as the velocity going out times the area, and from energy equations, velocity is square root of 2gh, and then for our purposes we're going to take out this radical 2g and then call this alpha. So we'll say that Q out equals alpha times the square root of h, and the area is just 1 meter squared. So first we're going to make derive the differential equation of the change in height with respect to time. So first we're going to look at mass balance. So the change in the mass of the system with respect to time equals the change of the mass going in with respect to time subtracted from the change in mass going out with respect to time. So we don't have any sort of explicit mass given, but we know that, I don't know if I mentioned, but we're working with water in this reactor. So we know the density of water is just 1 gram per meter cubed, or centimeter cubed. So we can take that into consideration, and we know that density equals mass over volume, so mass equals density times the volume. We don't explicitly know the volume, but we do have variables for the height and the area, so this can just be expressed as the density times the area times the height, because area times height equals the volume. So we can say, and also since area is completely constant, we're going to put that in front of the differential. So we have the change in density times the height divided by with respect to time. And then for the right hand side of the equation, we can express this as the flow rate times the density, because the units on density is grams per meter cubed. The units for flow rate is grams per second. So, wait a minute. It's meters cubed per second. So when you multiply these two, you're left with grams per second. Yeah. I'm going to erase this just to clear up some space. So like I was saying, we can multiply the flow rate going in times the density going in. And then same thing here, except for we're going to use alpha times the square root of h as the flow rate going out. So we'll say alpha square root of h, and then times the density going out. For simplification, we're going to say that the density of the whole system is the same as the density of the water going in and the density of the water going out. So these cancel, and then we're left with this. And then we're almost there. We just have to divide both sides by the area. And then we have the differential equation of height with respect to time, and that's the flow rate going in minus the flow rate going out, and in this case we express that as alpha, a constant essentially, times the square root of the height divided by the area. So now we need to derive the differential equation for the change in temperature, and we can kind of start doing the same thing, except for we're going to look at energy balance, and essentially the change in the energy of the system times the mass of the system equals all of the energy going in minus all the energy going out plus the non-flow work and the heat. However, we're going to say that the kinetic and potential energy is going to be negligible, and that there's no heat going to be added, or no heat change, and then there's going to be no non-flow work that we need to account for. So we're just essentially left with enthalpy. So this looks like, oops. So on the right hand side of the equation, it's the change in mass going in times enthalpy going in. Enthalpy will represent with capital H minus that going out respect to time. So we can substitute the mass again like we did above. So we can say that U represents the internal energy. So this is just the density times the area times the height. Height is lowercase h, enthalpy is capital H, dt equals, and then this equals the change in the mass going in is the flow rate going in times the density going in. We'll cancel the densities in a second. Times the enthalpy going in minus alpha radical H density going out times the enthalpy out. So we're going to cancel the densities. We can pull out the area in front. But there are also two equations that are very important to note that tie in temperature, and that is that relates the specific heat with the change in the internal energy and the change in enthalpies. So the change in internal energy equals the specific heat at a constant volume dt, and then the enthalpy change, the differential of enthalpy equals the specific heat at a constant pressure dt, or these are capital T for temperature. So basically, if you kind of integrate, you're left with the internal energy of the system minus some reference internal energy, and this equals the specific heat at a constant volume times a temperature subtracted from a reference temperature. And same thing kind of for the enthalpy here. So I'll just say enthalpy minus a reference However, for these references, we can set to whatever we'd like. They'll ultimately cancel. So we can set them to 0. And then we're ultimately left with that the internal energy of the system equals constant volume specific heat times the temperature. And then the enthalpy equals specific heat at a constant pressure times the temperature. And then also there's something else to note, that for liquids and solids, the specific heats at constant volume and constant pressure are equal. So we'll cancel those out once we put those into the equation. So let's keep writing down this here. So the area comes out front. We're going to substitute in our this equation here onto the left-hand side. So we're left with I pulled out the specific heat for the constant volume out because it's constant, and then the temperature and height are still in the differential because they change. And this equals the flow rate going in, and then the enthalpy going in is just specific heat at a constant pressure times the temperature going in minus alpha radical H, and then Cp, and then for the T going out, we'll just call that T. So here we have Cv, Cp, Cp, but like I was saying, those are equal because for liquids and solids, those are equivalent, and we're working with water, which is a liquid in our situation. So these cancel. So we're left with A times dHT dt equals flow rate going in times the temperature going in minus alpha radical H times the temperature. So we're getting very close. Our end goal is to get d capital T over d lowercase t. So right here, on this left hand, we can separate this. Let me divide by the area first. So we can separate this differential over here. So we get h dt dt plus t dh dt equals the same right hand side because we haven't done anything new to that yet. And then we just use algebra to get dt dt. We subtract the temperature times the change in height over time here, and then we divide by h. So I'll multiply by 1 over h, and then this is our final differential equation for the change in temperature with respect to time for this reactor. So now that we have this equation and now this equation for this reactor, we can go into Python and use the initial values that we are given to plot two different graphs that show the relationship for 100 seconds. So we'll jump right into Python now. Alright, so now that we have our two differential equations for the change in height and the change in temperature with respect to time for the reactor, these are our initial values. So our area is 1 meter cubed. The flow rate going in is 1 meter cubed per second. Alpha we have designated as 0.4. The initial height is 1 meter. The temperature going in is 320 Kelvin, and the initial temperature is 300 Kelvin. And then our end goal is to make two plots from 0 to 100 seconds for the change in height and the change in temperature. So with this, we're going to first start and define a function. So we're going to define a function and we'll call it HT for height and temperature. We need parameters. We need two parameters. We're going to need time and then just kind of a dummy variable. Call it K. So now we need to unpack the height and the temperature to equal this K. And then we can input our two differential equations. So our first one, we'll call dH for dHdt. That equals, looking at my iPad here, the flow rate going in minus alpha times the square root of height divided by the area, and then the change differential for the temperature is equal to the flow rate going in times the temperature going in minus alpha times the square root of the height times temperature, and this is divided by the area, and then subtract this also by temperature times dH dt, and then this is all divided by the height. So we want the function to return an array of dH and dt. So now we can use this here. This is the initial value solver. So I'll make the variable just called SOL for solution, and then we'll start. So first we need to say what function we're using. It's called HT. The time span is going to be from 0 to t end. Our end time is 100 seconds. Our initial values is an array. So first we used height, so we have to put in our initial height, and then our initial temperature. And then next, the method of integration we're going to be using is this one. And then finally, we need to say that our dense output will be true. And then if we do .sol, that grabs the solution and stores it into our variable here. So if we look, we can't tell much right now, but if we were to put in a time, it would give us values for both the height and the temperature. First, we need to make kind of an array of points from 0 to 100. We'll call it t-plot, because we'll ultimately use that in our scatter plot. And then we'll use NumPy's linspace from 0 to 100, and we'll do 500 points. And then if we do, we can unpack h and t to equal the solution at t for t plot. That will give us all of these points for height, and then I could do the same thing for the temperature. So now we are ready to plot. So first we are going to make subplots. We want one row, 2 columns, and then we're going to add 2 scatters. Our first will be for the height, so our x will be the t-plot for all the time points, and then our y is going to be the height, and then it's just for row 1, column 1, and then we'll name this dh dt, and then same thing for the temperature, except for we're changing our y-axis to be for the temperatures, and then the column will set for 2, and then it's dt dt. So let's see how this looks. And as you can see on the left, this is showing the relationship of the change in height with respect to time, and then on the right side, that is the change in temperature with respect to time. So this is part 1. Our next part, we're going to be looking more at concentrations and everything. So we're going to go back onto my iPad for that one. Okay, so now we're looking at the same tank. However, we want to look at the relationship between the water level and the concentration of a solute that's being mixed in this reactor. So unlike before, when we were kind of looking at temperature, there's going to be a specific concentration going in, and then there's the concentration inside of the reactor. However, the stir is ensuring that the concentration inside of the system will equal the concentration going out. So that's just something to keep in mind in this situation. So we need to derive a differential equation for the changing concentration with respect to time. So we can kind of start and go with a mass balance like we did previously with the first part of this problem. So we can say that the change in the mass of the system with respect to time equals the change in the mass going in minus the change in the mass going out. And now when we're going to substitute the mass, instead of the density, we're going to use concentration. So this works in place of mass because the units end up canceling out, so then we're left still with just kilograms, because the units for concentration are kilogram per meter cubed. That's what we're given with the initial values. And then area times height, that's meters cubed, so we're left with kilograms. And then similarly, it will be this instead of the density. And then we still have this alpha substitution, alpha times the square root of the height. So we'll call C out just C because it matches the concentration of the system, which we have on the left side. So there's that. Pull the area out because that's constant. And essentially we're going to get the same or a similar equation for what we derive for or not height, for the temperature. So we're going to divide by the area. And then separate these. And then we finally use some algebra to get, that's really bad, sorry, the differential for concentration. We subtract the height times the, concentration times the height differential, and then divide by the height. So if we look over here, this is essentially the same equation except for wherever there is the temperature, it's just concentration. So looking at that, we can alter the variables within the code that we already have and plot this in Python. So here's our code that we had previously. I just added the initial values for this problem. I don't need to repeat. It's just, actually, I'll leave it just since I repeated the other ones. But we can essentially just copy these parts. We're going to have to rename the name, give this a new function name. So we'll give this HC, and then change these variables here. So now where dt was, we're going to have to replace all of these with C for concentration. And then same thing here. I'll call this solution 2. And then we're going to look at our height and concentration function. Same time span, however with initial concentration. And then we can, we still have to do this here, but we don't have to set up another set of time points because it doesn't change with our problem. And then I can copy this here and call this, copy this here and call this fig2. And then for the second one, just change this out for the concentration, change the name of that, and then we're going to plot it and see what this looks like. So on the left, we still have the height with respect to time, and then now on the right side, we have the concentration, the change in concentration with respect to time. And notice how the x-axis is the same. However, the y-axis is different. This graph is the same because our initial conditions haven't changed for the height, but for the y-axis on the second plots for both of these are different. So this is measured in Kelvin, whereas this is in kilograms per meter cubed. So yeah, this is looking at first the relationship between the change in the water level and temperature for a non-steady state mass flow, and then same thing here except for just the change in the water level with concentration. So yeah, thank you for watching.